Hello students, I hope you all are doing good. Today we will discuss some important topics of wave optics chapter. In this lecture we will cover NCERT section 10.7 and example 10.2 from NCERT. This is the disclaimer. So students, today we are going to explore the fascinating topic of wave optics, specifically focusing on what you will be able to understand after this lecture. This sets the stage for our discussion on the behavior of light waves and their unique properties. Okay, so after this lecture, you will be able to understand the concept of polarization. So, polarization refers to orientation of light waves, and we will explore how polarizers can filter light waves based on their direction. We will also discuss Malus law, okay, which describes how the intensity of polarized light changes as it passes through a polarizer. Okay, so these topics you will be able to understand at the end of the lecture. So this is our index from. Okay, so we are going to cover NCERT section 10.7, which is polarization, and after that we will discuss example 10.2. Okay, so example 10.2 will help us see how polarized light can be used in practical scenarios. So students, we will understand transverse and longitudinal waves in this slide. Okay, our objective is to understand the fundamental differences between these two types of waves. So a wave is essentially a disturbance that travels through a medium such as water, air, or solid matter, or even through space. Notice how the term disturbance is highlighted here, emphasizing that waves are all about movement and change. So waves are remarkable because they transfer energy from one point to another without causing any permanent displacement of the medium itself. Okay, this means that while the energy moves, the medium through which it travels remains largely unchanged. Every wave involves some form of oscillation or vibration. This is a key characteristic of waves, and it's what allows them to transfer energy. Let's look at some examples of these oscillations. So first consider sound waves. In sound waves, the oscillation occurs through pressure variations. This is how sound travels through air, allowing us to hear. Okay, so sound waves create pressure variations. There is compression and rarefaction, okay, in the medium, due to which sound wave travels and it reaches our ears. Oh, it reaches our ears. Okay, and we can hear the sound waves. Okay, that compression and rarefaction and pressure variations in the air causes our eardrum to vibrate, due to which we can hear. So next we have electromagnetic waves or EM waves. These waves involve oscillations of electric and magnetic fields. This is crucial for understanding how light and other forms of electromagnetic radiations propagate. Finally, let's look at water waves. Here the oscillation is seen in the up and down motion of water particles. This is a more visual example of how waves can cause movement without permanently displacing the medium. So continuing with the understanding of transverse and longitudinal waves. So notice the image here which visually represents these two types of waves. This will help us understand how particles in a medium move differently depending on the type of wave. So let's start by examining longitudinal waves. In these waves, the particles of the medium vibrate parallel to the direction of wave propagation. This means that as the wave moves, the particle move back and forth in the same direction as the wave. Okay, so they move back and forth in the same direction as the wave propagation. This is a key characteristic of longitudinal waves. A common example of longitudinal waves is sound waves. Okay, when you speak, the sound waves travel through the air by compressing and rarefying the air particles in the direction of the wave. This is why sound can travel through different mediums like air, water, and solids. Now let's discuss transfer waves. So in these waves, the particles of the medium vibrate perpendicular to the direction of wave propagation. Okay, this means the particles move up and down or side to side, creating a wave pattern that is at right angles to the direction of the wave as wave travels. So particles vibrate in the direction perpendicular to the direction of wave propagation. So example of transfer waves include water waves and light waves. In water waves, the water particles move up and down as the wave travels across the surface. Similarly, light waves are transverse waves that can travel through vacuum, unlike sound waves. Okay, electric field vector and magnetic field vector. Both these vector oscillate perpendicular to the direction of propagation, and also these two vectors are mutually perpendicular to each other. The vibrations, the oscillation of these two vectors, magnetic field and electric field vector, are mutually perpendicular and also perpendicular to the direction of propagation. That's why light wave is also transverse wave. Now we'll discuss polarized waves in wave optics. Our objective is to understand what a polarized wave is and how it differs from an unpolarized wave. Okay, take a look at the image on the slide which shows both polarized and unpolarized waves. Notice how the polarized wave have a specific pattern while unpolarized wave does not. So let's see into what a polarized wave is. A polarized wave is a type of transverse wave where the vibrations or oscillations are restricted to a single plane or pattern. This means that instead of vibrating in all possible directions perpendicular to wave's direction of travel or wave's direction of propagation, the vibrations are confined to one specific direction. This is a key characteristic that distinguishes polarized wave from unpolarized ones. Now let's consider electromagnetic waves or EM waves, which include light. In these waves, the vibrations are actually the oscillation of electric field vector, often referred as light vector. This concept is crucial because it helps us understand how light can be manipulated and used in various applications, such as in polarized sunglasses or in photography to reduce glare. Okay, so polarization application of polarization is photography to reduce glare, also in the sunglasses to reduce the intensity of light. Also, polarization phenomenon is used in 3D glasses. Okay, when we go to watch a movie in the theater or a 3D movie, some sunglasses, special sunglasses to see the 3D effect is given. Okay, so that sunglasses, what is the phenomenon happening due to that sunglasses is polarization. Okay, due to which we saw the horizontal and vertical. We saw the horizontal and vertical components differently. Okay, due to which our eye process the horizontal and vertical component differently, and due to which we saw the 3D effect. Okay, now we will discuss unpolarized wave and differences between polarized and unpolarized wave. Our objective is to understand the difference between these two type of waves. Okay, so let's focus on polarized wave. To achieve a polarized wave, we need to confine or restrict the vibration of the electric field in a single plane or a pattern. This means that the wave's electric field is oriented in one specific direction. Imagine a wave moving through a narrow slit, allowing only vibrations in one direction to pass through. Okay, in the image you can see vibration of electric field vector or light vector. Why we are only taking electric field vector, not taking magnetic field vector? Because we have discussed in electromagnetic waves that magnitude of magnetic field vector is very small, much smaller as compared to the magnitude of electric field vector, because amplitude of electric field, that is E naught, is equal to C times B naught. Okay, means magnitude or amplitude of electric field vector is C times, C means 3 into 10 raised power 8 meter per second, a huge term. Okay, this term multiplied by the magnitude amplitude of magnetic field. Okay, that's why the major effect in the polarization is due to electric field. Okay, that's why we are taking electric field vector, also called light vector. So all the properties that is being shown by the light, that is polarization, okay, diffraction, so this is due to the majorly due to the electric field vector. Okay, so you can see the vibrations oscillation of electric field vector are in all direction before passing through the polarizer 1. Okay, in the diagram, after passing through the polarizer 1 or after passing through a slit, narrow slit, the vibrations are confined to only vertical direction and all other vibrations are blocked. So that is vertically polarized light wave. So this means the wave's electric field is oriented in one specific direction. Imagine a wave moving through a narrow slit, allowing only vibrations in one direction to pass through. Now let's discuss unpolarized light. So unpolarized light is characterized by its electric field vector vibrating randomly in all directions perpendicular to the direction of propagation. This randomness means that the light does not have a specific orientation. Think of it like a crowd of people moving in all the directions at once without any specific pattern. Now we'll study variation of plane polarized waves. Our objective is to understand how these waves vary. Okay, take a look at the image on the slide which shows a sinusoidal wave propagating in the positive x direction. This will be our reference as we discuss wave motion. So let's start by considering a simple experiment. Imagine holding a long string horizontally with one fixed axis, one fixed end. By moving the free end up and down, you create a wave motion. Okay, so this is a fundamental way to visualize how waves are generated and propagated. So as you continue to move the string, the wave you generate travels along the string in the positive x direction. This is an example of wave propagation where the energy is transferred from one point to another along the medium. So notice how this periodic movement of your hand creates a traveling wave that moves away from the source. This is a key characteristic of waves. They carry energy away from the source. In this case, your hand through the medium, which is the string. So finally, let's examine figure 10.17a again. It represents the wave at two different times, t equal to 0 and t equal to delta t. Okay, where delta t is greater than 0. This illustrates how the wave changes position over time, helping us understand the dynamic nature of wave motion. Okay, so the periodic motion of wave will create a traveling wave that moves away from the source. In this case, it is your hand. Okay, so your hand is producing the waves. Your up and down motion of your hand and you are holding one end of string is creating the waves. So wave is moving away from your hand. Okay, and figure is representing wave at two different times. Okay, so position over time. So wave changes position over time. Okay, so this helps us understand the dynamic nature of wave motion. Now we will study the mathematical equation of the plane polarized wave. Okay, our objective is to understand how this wave is represented mathematically. So let's start by introducing the wave equation. This equation describes the motion of a traveling wave. It's important because it helps us understand how waves move through different media like a string or air. So here is the wave equation. Yxt means displacement of wave is a function of position and time. x means position and t means time. So displacement is both function of position and time. Okay, so displacement is represented, displacement at any time t is represented by the x position. Okay, so any if you want to find the displacement of wave at any point, you have to define the position and time also. Okay, so after what time the position of this particular displacement is this, and after what time. Okay, so displacement of wave is a function of position and time both. Like its equation is a sine kx minus omega t. Okay, so kx, this factor representing the position, and omega t is the time dependence. Okay, so in this equation, y represents the displacement of the wave at position x and time t. Okay, here a is the amplitude which tells us how high the wave peaks are. So notice how this equation shows the disturbance propagating through the medium. The term kx minus omega t indicates the wave's movement over time and space. Okay, so which is important for understanding how wave travel. Now let's break down the components of equation further. The a is the amplitude, which is maximum displacement from the rest position. The omega is the angular frequency, calculated as 2 pi times the frequency nu. Next, we have another important equation, lambda equal to 2 pi upon k. This equation defines the wavelength lambda, which is distance between the consecutive peaks of the wave, distance between the two crests, or distance between the two troughs. Okay, finally, let's understand the relationship between the wavelength and wave number. The k is the wave number, which is related to the wavelength. Okay, this relationship helps us quantify how many waves cycle fit into a given distance. So let's examine the first key point. The displacement of the wave is along the y direction and is perpendicular to the direction of wave propagation. This characteristic make it a transverse wave. Remember, in transverse wave, the displacement is always at the right angles to the direction of propagation. Now, since the displacement occur in y direction, we refer to this wave as a y polarized wave. This terminology helps us specify the direction of wave oscillation. It's important to understand that direction of polarization indicates the orientation of wave electric field vector. Okay, so orientation of, or we can say oscillation of electric field vector is along y axis. So this is y polarized light. Okay, notice how the plane of vibration is confined to xy plane. Okay, vibration or oscillation of this wave is confined to xy plane only. Okay, vibrations or oscillation is not in z direction. So oscillation is along y direction, but it is represented by y's function of time and position both. That's why vibrations are confined to xy plane. This means the wave is linearly, or we can say plane polarized. In a plane polarized wave, the vibration occur in a single plane, which is important feature. So we can use linearly polarized or plane polarized interchangeably. So in a similar manner, we can consider vibrations occurring in xz plane. This would generate the z polarized wave. So x is the direction of propagation and z is the direction of oscillation of electric field. Okay, so this would generate a z polarized wave. This shows us how polarization can occur in different planes depending on the orientation of the wave's oscillation. Here is the mathematical expression for the displacement of a z polarized wave. Okay, so zx t equals to a sine kx minus omega t. In this equation, a represents the amplitude, k is the wave number, x is the position, and omega is the angular frequency, and t is the time. Okay, so z is a function of position and time both. So when we consider displacement in z direction, then we can say the wave is z polarized. Okay, so this formula help us quantify the wave's behavior in terms of displacement over time and space. So student, now we will study the time variation of plane polarized wave. Our objective is to understand how the displacement of a wave changes over a time at a specific point. If we consider a specific point, if we restrict the position dependence of wave, means we are considering only one point. At a one point, a traveling wave is considered. Okay, so we will see the time variation now of plane polarized wave. Okay, so our objective is to understand how the displacement of wave changes over time at a specific point. Take a look at the image which shows a sinusoidal wave moving in the position x direction. Notice how the curve represents the wave's displacement as at x equal to 0. So let's focus on the figure 10.17b. This figure illustrates how the wave's displacement changes over time at a position x equals to 0. Imagine this as a snapshot of the wave at a specific point. It's important to understand that this displacement is a key characteristic of wave motion, showing us how energy is transferred through the medium. Now, picture watching a point on the wave. Okay, now you are watching, or imagine that you are watching a point on the wave. It moves up and down smoothly, much like a swinging pendulum. This motion is continuous and rhythmic, which is a fundamental property of waves. By visualizing this, we can better grasp how waves propagate through space. If you were to stand at one spot, say x equals to 0, you would observe this up and down motion repeating perfectly after a certain interval of time. Okay, that is the time period of wave. So this repetition is known as the waves period, and it's crucial for understanding waves behavior. So let's examine what happens if we observe another point further along the wave at x equals to delta x. You will notice that this point exhibits the same up and down pattern as the initial point, that is x equal to 0. Okay, it will exhibit the same pattern, up and down pattern, similar to the initial position. Initial position was x equal to 0. So this is a important characteristic of waves, that is they repeat their pattern over space. So continuing with the variation of plane polarized wave, take a look at the image. Okay, so however, this second spot starts its motion slightly later of the first spot. Okay, so if we are considering two spots at x equal to 0 and at x equal to delta x, okay, so at both these spots, okay, they are exhibiting same up and down motion, but the second spot start its motion slightly later the first spot. So this delay in the wave motion at different points is known as a phase shift. Now student, what is shift in a phase? Is the amount by which a wave is shifted horizontally from a reference point. Okay, in the A diagram you have seen one wave is represented by bold line, one is represented by dashed line. So this is a phase shift. So after some time, the motion up and down motion is same at every point, but at every spot this motion is separated by some time. Okay, so at x equal to delta x, the motion is delayed by some amount, some time. Okay, so this delay is known as phase shift. Okay, now we will study the concept of polarizer. Our objective is to understand how a polarizer works. Notice the image of a Polaroid, which is a device that selectively transmits one of the two orthogonal components of light. So let's examine the transverse nature of light. A Polaroid is a device that can demonstrate this property. It's important to note that light waves are transverse, meaning their oscillation are perpendicular to the direction of propagation. This characteristic is what allows Polaroids to function effectively. So let's study into the structure of a polarized Polaroid. It consists of a long chain molecules aligned in a specific direction. This alignment is a key because it determines which component of the light wave will be transmitted. Think of it like a comb that only lets certain strands of hair pass through. Okay, notice how the electric field vectors of the light wave interact with the Polaroid. The vectors that align with the direction of the molecules get absorbed. This selective absorption is what allows the Polaroid to filter light, letting only certain orientations of electric field pass through. So finally, let's define what a polarizer is. A polarizer is a device that transforms unpolarized light into polarized light. This process is essential in many optical applications, such as reducing glare in sunglasses or enhancing contrast in photography. Okay, so Polaroids are also used in windows of airplanes, okay, to reduce the intensity of light coming through. Okay, also in the sunglasses, also in the photography. So, what is polarizer? So, Polaroid is named polarizer for a specific function. Okay, it is basically a Polaroid. So, polarizer is basically a Polaroid, and we can use the term in this chapter. Sometimes we will use Polaroid, sometimes we will use polarizer. So, what is polarizer? It is a special function Polaroid. Okay, so light is being polarized through passing through the Polaroid. Okay, so its function is to polarize the light. Okay, that's why it is called polarizer. When we analyze the intensity coming through polarizer, then that Polaroid will be called analyzer. Okay, so basically polarizer is a special function Polaroid. So continuing with the concept of polarizer, so Polaroid works to selectively transmit the light. So let's delve deeper into what happens when unpolarized light hits a Polaroid. The Polaroid acts as a filter, and as a result, the light wave becomes linearly polarized. This means that the light is now oscillating in a single plane. It's important to understand this transformation as it forms the basis for many optical technologies. Now observe how the electric vector of the light waves behave. It oscillates along a direction that is perpendicular to the aligned molecules in the Polaroid. Okay, this means this alignment is crucial because it determines the direction of polarized light. Notice how this selective transmission affects the light properties. Okay, so electric vector will oscillate along a direction perpendicular to the aligned molecules, and electric field vector, oscillations of electric field vector that are along the aligned molecules, aligned chained molecules, will be absorbed, and perpendicular to the aligned molecules will be transmitted. Okay, so what happens when light passes through a polarizer? So light waves become linearly polarized, meaning the electric vector of light oscillates in specific direction. This direction is perpendicular to the alignment of molecules in the polarizer. Okay, so here we have a visual representation of unpolarized light passing through a Polaroid. This image helps us understand the process of polarization. As you can see, the light entering the Polaroid is unpolarized, and the Polaroid filters the light, allowing only certain oscillations to pass through. This is a key concept in understanding how polarizers work. Now let's focus on the axis of the Polaroid. The axis along which the Polaroid allows the oscillation of the electric field vector is known as pass axis or transmission axis. Okay, if the Polaroid is allowing the oscillation of electric field vector in the y direction, then y axis is the transmission axis of this Polaroid. Okay, so this axis is crucial because it determines the direction of which in which the light is polarized. So Polaroid transmits light with electric field vectors oscillating parallel to its transmission axis while blocking the perpendicular components. This selective transmission is what gives Polaroids their unique ability to polarize light. Notice how the alignment of the transmission axis is key to this process. Finally, let's consider the intensity of light after it passes through a polarizer. Since the components of electric vector are reduced, the intensity of the light also decreases. This reduction in intensity is an important aspect of polarization as it affects how we perceive light after it has been polarized. Now we'll see the effect of polarizer. Our objective is to understand how light behaves when it passes through Polaroids. Take a look at the figure 10.18, which shows light passing through two Polaroids, P2 and P1. Notice how the transmitted light changes as the angle between them varies from 0 to 90 degree. So let's start by considering what happens when unpolarized light such as that from a sodium lamp passes through a single Polaroid labeled P1. The first thing to note that is the intensity of the light drops to half. This is because the Polaroid only allows light wave oscillating in one direction to pass through, effectively filtering out the half of the light. Okay, so observe that rotating P1 doesn't change this reduced intensity. Okay, this is an important point. So light intensity drops to half. Okay, so rotating this P1 will not change the reduced intensity. Okay, intensity will be reduced to half when it is passing through a Polaroid P1. It is reduced to half. So if we are rotating P1, so it will have no effect on the reduced intensity. Intensity will be half again. So now we'll study variation of intensity through two polarizers. Our objective is to understand this variation using a simple setup. Take a look at the image provided, which shows two Polaroids labeled P1 and P2. Notice how they are positioned relative to each other. This setup helps us visualize the changes in the light intensity. You can see there are two axes. One is passing through P1, one is passing through P2, and the angle between the axes of both his Polaroids is theta. Okay, so that axes are transmission axis of two Polaroids, or we can say pass axis. So let's start by adding a second Polaroid before P1. This is an important step because it sets the stage for observing how light behaves when it encounters multiple polarizers. Initially, light will pass through P2 and this will reduce its intensity. Okay, keep in mind that orientation of P2 affects how much light gets through. Now as light passes through P2, let's focus on what happens next. When we rotate P1, there will be a specific position where no light will pass through both P2 and P1. Okay, this results in complete darkness. It's crucial to understand that this occurs because the polarizers are aligned in such a way that they block all the light. Continuing from the position of complete darkness, if we rotate P1 by 90 degrees, something interesting happens. P1 will now transmit nearly the full intensity of light that emerges from P2. This clearly tells us how the relative orientation of polarizers can significantly affect the amount of light that passes through. Okay, so for one position, no light will transmit through P2, that is complete darkness. Okay, and when P1 is rotated by 90 degree from the complete darkness position, then P1 transmits nearly the full intensity of light emerging from P2. Now consider the light passing through the second Polaroid P2. This light becomes polarized along the pass axis of P2. It's important to understand that this polarization is a key step in how the light intensity will change as it moves through the system. This polarized light reaches the first polaroid P1. Here the path axis of P1 is at an angle theta compared to P2's path axis. Okay, so the angle between path axis of P1 and P2 is theta. So this angle is critical because it determines how much the light intensity will be transmitted through P1. So let's talk about the amplitude of the light after it passes through P2. We denote this amplitude as E. Okay, so light after passing through the P2 Polaroid, so intensity, or sorry, we say amplitude of the light passing through P2 is E. This amplitude can be resolved into components like E cos theta and E sin theta. Okay, so it's important to remember that the intensity of light is proportional to the square of its amplitude. This relationship is fundamental in wave optics and helps us predict how the light's intensity will change as it passes through the polarizer. Now, what does this mean for the intensity of light passing through P2? Okay, we denote this intensity as I naught. Okay, I naught proportional to the square of amplitude. Since intensity is proportional to square of amplitude, so intensity passing through P2, that is I naught, will be proportional to E square, that is the amplitude of light passing through P2. So second Polaroid labeled as P1 is also known as analyzer. Okay, so Polaroid polarizer is a special function Polaroid that is used to polarize the light, and analyzer is also special function Polaroid that is used to analyze the light that is polarized by P2. Okay, so P1 is known as P1 Polaroid is known as analyzer. This is because it helps us analyze the properties of polarized light. The analyzer plays a crucial role in determining the intensity of light that passes through. So it's important to understand its function. So let's break down the components of electric field E. The component E cos theta aligns with the path axis of P1. Okay, and E sin theta is perpendicular to the path axis of P1. Okay, so this distinction is key to understanding how the light's intensity is affected as it passes through the analyzer. Only the component E cos theta that aligns with the path axis of P1 will actually pass through. So P1 will allow only E cos theta because it is along the path axis of P1. Okay, but it will block the E sin theta because it is perpendicular to the path axis of P1. Okay, so this means the orientation of analyzer directly influences the amount of light that gets through. So now let's consider the intensity of light after it passes through P1. The intensity is directly related to the component of electric field that aligns with the path axis. Okay, so the intensity of light after passing through P1 is proportional to, so what is the amplitude of light that passes through P1 is E cos theta. E sin theta is blocked. Okay, so E cos theta is transmitted through P1. So amplitude of light transmitted through P1 is E cos theta. So intensity of light that is transmitted through P1 will be proportional to the amplitude E cos theta square. Okay, so I proportional to E square cos square theta shows us how the intensity depends on both the electric field and angle theta. So as we revealed previously, notice that we are focusing on the intensity of light after it passes through each polarizer. The key point here is that intensity changes as light moves from P2 and then P1. So let's look at the equations that we have discussed. So this describes this intensity. Initially the intensity I naught is proportional to the square of electric field E, represented as I naught equals to K E square. Okay, after passing through a polarizer or analyzer, the intensity I is proportional to E square cos square theta, which is equal to I equals to, or we can say I equal to, after removing the proportionality sign, k E square cos square theta, where k is the constant of proportionality. Okay, so we introduce the constant of proportionality k. It's important to understand that k is a factor that relates the electric field to the intensity of light. So let's divide the equation we just discussed. So by dividing these equations, we arrive at I upon I naught equal to k E square cos square theta upon k E square. So k E square and k E square from numerator and denominator will get cancel out. And after simplifying, this simplification leads us to equation I equals to I naught cos square theta. And this is equation 10.18, which is a fundamental result in wave optics. This equation shows us how the intensity of light changes based on the angle theta. Okay, so this relationship is known as Malus law. It's a fundamental principle in optics that describe how light intensity varies with the angle between the light's initial polarization and the polarizer's axis. Okay, now we'll understand Malus law. We'll explore Malus law, which is a fundamental concept in wave optics. Our objective is to understand how the intensity of light changes when it passing through the polarizing materials. So let's take a look at the figure showing two Polaroids P1 and P2 with their transmission axis at an angle theta. Okay, so transmission axis of first Polaroid is vertical and transmission axis of second Polaroid is at angle theta with the transmission axis of first Polaroid. So notice how the angle between these axes is crucial for determining the intensity of light that passes through. So let's delve into Malus law itself. When a beam of completely plane polarized light passes through an analyzer, the intensity of transmitted light depends on the angle between the polarizer and the analyzer. So first polarizer P1 is known as polarizer, and second Polaroid that is used to analyze the light that is coming from polarizer is known as analyzer. So this law is essential for understanding how polarized light is used in technologies like sunglasses and camera filters. So according to Malus law, the intensity I of transmitted light varies as the square of the cosine of angle theta between the transmission axis. This means that as the angle changes, the intensity follows a predictable pattern. Okay. So now we'll understand the transmitted intensity is how transmitted intensity is calculated using Malus law. So Malus law tells us how much light passes through polarizing filters based on the angle between their pass axes. Notice the emphasis on the angle as it plays a critical role in determining the initial intensity of transmitted light. The formula we will use is I equals to I naught cos square theta. Okay, so this is the formula I equal to I naught cos square theta. Okay, so I represents the intensity of light after passing through the second Polaroid, that is analyzer. Okay, I naught is the intensity after passing through the first Polaroid, that is polarizer. Okay, and theta is the angle between the transmission axis of polarizer and analyzer. Okay, so again figure is represented. So in this figure, I naught is the intensity of light passing through the polarizer P1 as represented, and after passing through P2 it will be I naught cos square theta. Okay, so let's examine what happens when unpolarized light hits a polarizer. Okay, the intensity of transmitted light is determined by averaging the cosine squared of the angle theta. Okay, so let's see. So when light is incident on first Polaroid, that is polarizer, okay, why intensity becomes half? Intensity of light becomes half after passing through the first polarizer. So let's see. So I transmitted equals to I UN. UN means unpolarized light multiplied by cos square theta average. Okay, so what is the I transmitted? So that is the intensity of light transmitted to first Polaroid P1, and which is equal to, according to Malus law, I unpolarized intensity of light that is incident on first Polaroid, and cos square theta, the angle between the oscillation of electric field and transmission axis of the first Polaroid. Okay, so oscillation is in all directions. So we'll take so theta will be having many values. So we will be taking, so theta will be, the oscillation is in all the directions. So theta will be having many values. So we will take the average of cos square theta. And we know that average of cos square theta function is half. We have discussed the average values of cos theta, sin theta, cos square theta, sin square theta in the alternating current also. So average function, so average of the cos square theta is half. So intensity of transmitted light through first Polaroid will be I UN, that is intensity of unpolarized light divided by 2. That is, it becomes half. Okay, so that is why intensity is reduced by half. Okay, so this reduction in intensity is why when unpolarized light passes through a polarizer, its intensity is halved. It's important to remember that this is a fundamental property of polarizer and help us understand how they filter light. Now we'll study more, okay, into the transmitted intensity using Malus law. So let's look at different cases of how light intensity is affected by the angle between the Polaroids. We will start by examining the scenario where the axes are parallel. This is when the angle theta between the polarizer and analyzer transmission axis is 0. Okay, so parallel axis. When angle theta is 0 degrees, okay, the output intensity is at maximum. This is because the light passes through both the Polaroid without any obstruction. This formula for this is I equals to I naught cos square theta. Okay. So output intensity will be I equal to I naught cos square theta. That is, so now angle is 0 degree, means angle between the transmission axis of two Polaroids, that is polarizer and analyzer, is 0 degree. Transmission axes are aligned in same direction. So theta is 0 degree. So I naught cos square 0 degree. So cos 0 is 1. So 1 square is 1. So I will be equal to I naught. That is the maximum transmission through the P2 Polaroid. Crossed axis, when angle between polarizer and analyzer is 90 degrees. That is the meaning of crossed axis. Means theta equal to 90 degree. So then output intensity will be I equal to I naught cos square 90 degree. So cos 90 is 0. So transmitted intensity through analyzer will be 0. Okay, we have discussed the cases that in one position there is complete darkness. That is the position when transmission axes are at 90 degree of both the Polaroids. Okay, and when we rotate the analyzer through 90 degree angle from this complete darkness position, then intensity is maximum. That is the case when axes become parallel. When transmission axis of both analyzer and polarizer become parallel, then the maximum transmission of light is there. So this is example 10.2 based on what we have discussed before. So you have to discuss the intensity of transmitted light when a Polaroid sheet is rotated between two crossed Polaroids. There are two crossed Polaroids, means the angle between the transmission axis between two Polaroids is 90 degree. Another Polaroid sheet is there between two crossed Polaroids and it is rotated. So discuss the intensity of transmitted light. So let's start by looking at this diagram. It shows the setup of our experiment with three Polaroids P1, P2 and P3. Notice how P1 and P3 are crossed, means the angle between the transmission axis of P1 and P3 is 90 degree, meaning their axes are perpendicular to each other. Okay, so consider the intensity of polarized light after it passes through the first polarizer P1. So we denote this initial intensity as I naught. This is the starting point from our analysis, and it's important to remember that this light is already polarized. Now we need to determine the intensity of light after it passes through the second polarizer P2. This is where things get interesting because the intensity will change based on the angle between the axes of P1 and P2. So according to Malus law, intensity of light passing through P2, that is given by IP2, equal to I naught cos square theta. Theta is the angle between transmission axes of P1 and P2, and I naught is the intensity that is transmitted through first Polaroid P1. Okay, now it is incidenting on second Polaroid. So after passing through second Polaroid, so what is the transmitted intensity will be IP2, which is equal to I naught cos square theta according to Malus law. So it's important to understand that theta represents the angle between the axes P1 and P2. So since P1 and P3 are crossed, the angle between their axes, pass axes, is 90 degree. Okay, this means that without any other polarizer in between, no light would pass through. However, by introducing P2 and rotating it, we can control the light intensity. So here we have an image again. So before the light reaches P3, its intensity is given by I naught multiplied by cos square theta. Now light is transmitted through P2. It is incidenting on P3. Now light that is incidenting on P3, its intensity is I naught cos square theta. Okay, and the angle between the pass axis of P1 and P3 is 90 degree. Okay, so angle between the pass axis of P2 and P3 is 90 minus theta. So angle between pass axis of P1 and P2 is theta, and angle between the pass axis of P1 and P3 is 90 degree. So angle between the pass axis of P2 and P3 will be 90 degree minus theta. Okay. Now intensity of light that is transmitted through or emerged through P3 according to Malus law. So IP3 will be equal to I naught cos square theta, that is the light incidenting on P3, and again cos square angle, cos square the angle that is between the transmission axis of P2 and P3, that is 90 minus theta. So I naught cos square theta, cos square 90 minus theta, again Malus law is applicable. Okay, so if there is one more Polaroid, we will apply the Malus law again. Okay, so this equation shows us how the intensity depends on the both initial intensity and the angles involved. So simplifying further, we find that IP3 equals to I naught multiplied by cos square theta sin square theta, because sin 90 minus theta is cos theta and cos 90 minus theta is sin theta. Okay, so that's why cos 90 minus theta is sin theta. So square is there, so sin square theta. Okay, so this step highlights the interplay between the sine and cosine function in determining light intensity. So finally, we can express the intensity IP3 equals to 1 upon 4 multiplied I naught 2 cos theta sin theta whole square. Okay, we have multiplied this equation with 4 and divided with 4. Okay, so 1 by 4 I naught and 4 cos square theta sin square theta, and we have taken the whole square, so it will become 2 cos theta sin theta whole square. Okay, now let's look at the equation again. Now we can simplify the equation to IP3 equals to I naught upon 4 multiplied by sin square 2 theta. Okay, So sine 2 theta is equal to 2 sine theta cos theta. So we have written sine 2 theta in place of 2 sine theta cos theta. Okay, so it will become sine square 2 theta. Okay, so this shows us the intensity is proportional to the square of the sine of twice the angle. Okay, so maximum value of sine square 2 theta is 1. This maximum occurs when theta equals to pi upon 4. So for pi upon 4, sine square 2 theta will be maximum, because pi upon 4 multiplied by 2 will become pi by 2. Sine pi by 2 is maximum 1. So 1 square 1. So maximum value of sine square 2 theta will be 1 when theta equal to pi by 4. So therefore the transmitted intensity will be maximum when theta equal to pi by 4. So to summarize everything that we have studied before or today's lecture, let's have a brief look on summarize points. Okay, so polarization demonstrates that light waves are transverse in nature. This means that the oscillations of light waves occur perpendicular to the direction of wave propagation. Let's explore how this property of light is crucial in understanding its behavior. Unpolarized light has electric field vector that vibrate randomly in all directions perpendicular to the direction of propagation. This randomness is what makes unpolarized light different from polarized light, which we will discuss next. Linearly polarized light, in this case, the electric field vector vibrate in a single direction perpendicular to a direction propagation. Okay, this uniformity in direction is what characterizes polarized light and is essential for various optical applications. Introducing the polarizer, which is a device that converts unpolarized light into polarized light through selective transmission by allowing only certain orientations of the electric field vector to pass through a polarizer, effectively filters the light, creating a more uniform wave. We have the analyzer, which is used to determine whether the light is polarized. By rotating the analyzer and observing changes in the light intensity, we can confirm the presence and orientation of the polarization. Malus law, which is fundamental in understanding light intensity through the polarizers. The law states that transmitted intensity I is equal to initial intensity I naught times the cos square the angle theta between the polarizer transmission axis of polarizer and analyzer. This relationship helps us predict how light behaves as it passes through three optical elements. When unpolarized light passes through a polarizer, the output intensity is reduced to half of the input intensity. This is because the polarizer allows half of the randomly oriented electric field vector to pass through, demonstrating the selective nature of polarization. So when the polarizer are parallel, okay, means polarizer and analyzer, or we can say two polarizers are parallel, means their transmission axes are parallel. So theta is 0 degree, give the maximum transmission of light through them. And when they are crossed, when the transmission axes of two polarizers are crossed, then the transmission of light through two polarizers is 0 when angle theta is equal to 90 degree. Okay, so now we will solve or see some practice questions. So if unpolarized light with an intensity 100 unit passes through a polarizer, what happens to its intensity? Okay, remember a polarizer. So what is the intensity of the transmitted polarized light? Remember, a polarizer only allows light waves aligned with its axis to pass through, reducing the intensity. So what happens when plane polarized light encounters an analyzer? Analyzer is rotated at 60 degree to the polarization axis. Okay, we need to determine the fraction of initial intensity that gets through. Okay, this involves understanding Malus law, which states that transmitted intensity I equals to I naught cos square theta. So for what angle between two polaroids will the transmitted intensity be 1/4 of the maximum possible transmitted intensity? So what is the nature of light, transverse or longitudinal? And what is the intensity of light transmitted through two crossed polaroids with perpendicular transmission axis? So you have to tell the intensity transmitted when two polaroids are crossed. Okay. So this is all about today's lecture. I hope you understood it well. Thank you.